Yes, so good afternoon, everyone. So do you hear me well? Welcome you all to our second Geo-Cluster webinar, which is titled Geothermal Exploration, Advanced Method and Technologies. It was nice to meet you all. My name is Yulia Demchuk, and I am a board member of Geothermal Ukraine, and a representative of a GeoSYN project, and I will be moderating today's event. And we are pleased to welcome you to join this afternoon dedicated to innovative approaches, tools, and technologies that are advancing geothermal exploration across Europe. And today's webinar brings together several Horizon Europe and international projects covering the full exploration chain. And this event is organized under the Geo-Cluster. It's a collaboration and knowledge exchange and project exchange platform connecting 11 projects working in geothermal energy and related fields. And a few organizational moments. So the webinar will run until 5:30. It's divided into 2 sessions with a coffee break, and we'll conclude with the joint Q&A sessions. So please feel free to post your questions or any comments you may have into the chat at any time during the webinar. So we will collect them for the discussion at the end of event. So I wish you engaging and inspiring event. So let's begin. And the first item of our agenda is an overview of this Horizon Europe projects. It's a GeoSyn, Urgent, FindHeat, Go Forward, and GeoHeat. I will start a very brief introduction of the GeoSyn projects and will share short presentations with you. So just a moment, please. So I hope it works. The GeoSyn project is a geothermal synergy enhancing industrial energy efficiency through steam high temperature heat pumps and heat powered cooling systems.
Now you're muted.
We can't hear you anymore.
Yeah.
And now it works?
Yep.
Good. Okay, so GeoSyn project is funded under Horizon Europe project with a duration of 3 years and ending on October 2027. And the total budget of the project is 3 million euros. So the next slide. So our consortium, it includes 10 partners from 5 countries, and it's from Italy. Our project coordinator, APRA, it's such organization and institution as Unifi, CoSwitch, RivaCold, and SMWF. The next one is from Norway. It's a Sinteft organizations. From Denmark, CDU, Southern University of Denmark. From France, now ECO. And from Ukraine, it's Geothermal Ukraine. So the main aim of our project is to develop a steam heat pump reaching more than 200 Celsius degrees, combined with heat power refrigeration system, which can deliver cooling down to 5 Celsius degrees. And the technology, it uses water as a refrigerant and cascade energy efficiency through the system, so extracting maximum value from energy from every degree of geothermal energy and geothermal heat. And the same heat source could be served both to cover heating and cooling needs of industries. And additional main objectives of our projects is to promote the adoption of geothermal energy among all sectors of industry where the technology could be applied, as well as increase awareness and public trust among the society. And to prove the reliability of our solution within the project, we are considered two case studies. The first one is a dairy factory in Italy to demonstrate the system works in real production processes and conditions. And the second one, it's a virtual case study. It's a cement plant in Ukraine to show that this technology works across different industrial applications as cement plant, as well as during the project, the 5 additional virtual case studies were selected from other industries like food, like paper plants, as well as other potential industrial applications to show the flexibility of the proposed solutions. And a few words about our GeoCluster. So as part of our communication and dissemination activity within our project, the GeoCluster was established during 2025. And it's an open community which was coordinated by Geothermal Ukraine under supervision of our project coordinator, it's APRA. And currently it gathers 11 and connects 11 projects. And as you might see on this slide, and the main aim and idea is to focus on ecosystem building, to mutual learning, to coordinated communication activities of the projects. We are open, we are free, so all our projects are welcome to join us. And the planned activities under the clusters as you see, include organizations of joint mobilization and mutual learning workshops. It's joint participations in events, joint webinars, and this event is actually a good example of our collaborations with other projects. And it's the next is to synchronize our efforts for common publications and social media campaign. So it's very brief about our GeoSyn. So thank you all, and I will now hand over the floor to Virginia Hercule-Emmanuel from Argent Project. So please go ahead with Argent presentation. Thank you.
Thank you very much, Julia. So I guess, right. Okay. Nope, sorry about that. So I guess you see my slide. That's okay? Yeah. All right, so as said, I'm Virginie Hercule-Emmanuel. I am the coordinator of the Urgent project, which was funded around under the Horizon Europe framework. So I'm happy to be here today because I participated already to the first joint mobilization and mutual learning workshop of the Geo-Cluster. And I felt a bit lonely because I was the only project representing geothermal exploration. And we proposed to have this second session so that exploration could also be the focus also of such workshops. So our Urgent project is focusing mainly on seismic exploration, and it stands for Sustainable and Affordable Urban Geothermal Exploration, Novel Technologies and Workflow. So I'm happy to be here today to give you a brief overview of this project. We are a team of 8 partners from 5 European countries. We have several SMEs on board, so technology developers, Seismic Mechatronics and InnoSeis. They will give 2 presentations today, which is very nice because you will see the achievements that we have currently when it comes to seismic technology developments. We also have 1 software developer, so it's DGB from the Netherlands, and they are providing software to help and support the interpretation of seismic data. And Real-Time Seismic, seismic service company from France, who is helping us with everything linked to design of survey, processing of data. And we have also Euroquality helping us and supporting us with everything linked to communication and dissemination. We also have a large industrial partner from Hungary, so it's small, originally looking mainly at oil and gas, but who is now also looking more and more into the potential of geothermal for Hungary. And we have also 2 research institutes, AGH in Poland and VITO, so coordinating the project. For this project, we have selected 3 test sites, 1 in Belgium, 1 in Hungary, and 1 in Poland. And this is to test mainly the development of the technology, but also the entire chain of solution that we will provide. So as said, the main objective is really looking at the entire seismic exploration chain. We have 5 specific objectives. One is looking at innovative acquisition technology. So it's to enable low impact, affordable, high quality seismic data acquisition to de-risk geothermal developments in key underexplored areas. And typically we are looking at urban areas. We also want to look at efficient data analysis. So we will acquire data, but we also want to make sure that we can improve reservoir characterization and fault detection to increase drilling success rate. Looking at risk management, and there we are specifically looking also at induced seismicity on how to reduce this risk. So we want to apply advanced modeling and simulation to ensure sustainable and long-term reservoir performance while managing the seismic risk. Looking at social engagement and environmental performance in urgent, we try to strengthen environmental performance and market uptake of the urgent developed solution while increasing engagement for geothermal energy at large. And at the end of the project, the goal is really to define proper exploration strategies for seismic exploration to de-risk geothermal projects. And that can be applicable in different geological contexts and for different reservoir depths. Here it's just to give you an idea of the different project results that we expect by the end of the project. The 2 first ones are about the technology. So one is on the prototype of the eVibe and the other one on the MEMS sensor. You will have presentation on these 2 project results in a few minutes. The 3rd one and the 4th one are linked to the activities mainly of real-time seismic, looking at optimizing survey design, but also at the processing of the acquired data. The 5th project result is the improvement of the existing OpenDetect machine learning solution and software. So it's DGB, looking at these aspects. The 6th one is a risk management toolbox. So it's mainly AGH and VITO trying to develop algorithm and methods and specific toolbox. You can already visit this VITO. It's on the VITO GitHub. And it's still under development, but we are progressing well on that one as well. And AGH together with VITO and the other partner are also looking at the identification and also reaching out to stakeholders and to make sure that the solution will be used and that we have a nice exploitation roadmap at the end of the project. And finally, as said, the last project result will be the integrated workflows that we will propose. The first 1.5 years of the project was mainly the technological software and method development, and we are now entering into a very exciting phase of the project with the testing on site and the validation of the technology. And I will stop here for the urgent presentation because I think you will hear more in the next presentation. I thank you very much for your attention.
Thank you very much, Virginia, for the urgent project overview. I would like to invite Alexandros Daniildis to present the FindHeat project.
We don't hear anything. Okay,
yeah.
Great.
So it's not Alex that is presenting today, but me. I'm Pierre-Olivier Brunat. I'm also from TU Delft, and I'm a co-PI in FindHeat. So the FindHeat project is a novel exploration toolkit for finding geothermal heat efficiently and sustainably. It's a consortium coordinated at the Delft University of Technology in the Netherlands, and we have partners from the UK, from Switzerland, Germany, Czech Republic, Iceland, France, and Spain. And the project is formally coordinated by Sebastian Geiger, who was not able to join today. This is why Alex and myself are doing the presentation on his behalf. So the content of the project, so in geothermal energy, we have issue, we have high economic and technical risk, negative public perception, geological uncertainty and success rate are below 50%. And what we want to do in the scope of the FindHeat project is to improve all of those aspects. So having low risk geothermal project, constraint uncertainty, positive public engagement, and success rate more than 65%. Concretely, how do we do this? So we provide a modular toolkit, what we call that the FindHeat toolkit, to enable geologically based geothermal resource assessment, minimize the economic and technical risk, improve the long-term performance, and catalyze a positive community engagement. And for this, we have different modules. So we will do software and methodological solutions. We will develop fundamental and site-specific conceptual models. We quantify economic benefits of those models, and we engage with local population and develop communication strategies and trainings. In terms of case study, we have 8 case studies in 6 different countries. Those case studies are for heat production or electricity production, and they are at different level of maturity in different geological settings. So for the heat production, we have the Litoměřice in Czech Republic. We have the Delft Sandstone project in the campus of Delft, UK GEOSYN in the UK, and the London case study as well. And for electricity production, we have the French case study, Rittersofen and Sulzes-Forêt, the Engil site in Iceland, and the Canary Island in Spain. We have also 2 PhD working on those different aspects. One PhD is more working into hot sedimentary aquifers, and she started with the Delft geothermal project, and she will soon move towards the UK sites. And the other PhD is focused on faulted system in Rittersofen, high enthalpy, and in Iceland. And that's it. Thank you for your attention for this small introduction. More will follow afterwards.
Yeah, many thanks, Pierre-Olivier, for FindHeat introduction. Let's now move on the go forward projects, and David Brown will provide us a brief introduction. So please, David, take the floor.
Paramita, if you're trying to speak, we cannot hear you. I see that you are unmuted, but we don't hear you.
Do you hear me now?
Yes, now we do.
Okay,
Thank you.
sorry. Yes, I was trying to speak. The usual problems.
Yes,
So I was
no
just
worries.
saying that it's not David Brun, it's me. So here again, I'm Paramita, and I'm the R&D manager and senior geoscientist at Swiss Geoenergy. It's an energy company based in Geneva. We are an associated partner in the Go Forward project. We are funded by the Swiss State Secretariat for Education, Research and Innovation. I'm very happy to be able to introduce the Go Forward project today. So Go Forward stands for Geothermal Exploration and Optimization through Forward Modeling and Resource Development. So we all know that geothermal energy can play a much larger role. We all agree that's why we are here today. However, the biggest hurdles or obstacles are related to the high upfront costs, lack of subsurface data, which leads to uncertain geological models. So here we know that one of the most widely used technique for property modeling, which is geostatistical interpolation. Basically, these are the models based on which we make decisions related to exploration, related to financing of geothermal projects. And very simply, if you see the left side of the model, you see how sparse could be the data. And ideally, the closer to the data, you have more confidence. And as soon as you go away from the data, your confidence in the model decreases. So the problem with this kind of technique is it's mathematically rigorous. However, it's data driven. And that's why it scales with data density. So the more the data, the better the model. And as soon as you move away, the less the informational value. So this is where actually Go Forward comes into picture. The umbrella idea is to make accurate pre-drilling predictions of geothermal reservoir properties. And what do we want to do is we want to create calibrated process-based forward models, which are enhanced by machine learning techniques. Now, by forward models, what we mean is that we move beyond interpolation, but we are trying to model the geological processes in time and predict the geothermal reservoir properties. The other objective is we are trying to work with open source codes and develop alternatives for subsurface modeling and validate them across different depositional environments, such as carbonate, sandstones, basement. And the third and one of the main ideas is that we want to create this framework which will then be used for quantifying uncertainties based on stochastic ensemble-based models and run techno-economic analysis, which will then help us to have quantified uncertainty quantified geothermal potential estimations. Now, how do we want to do this? Is we are developing, as I said, forward modeling techniques. And there are three principal techniques where we are focusing. One is stratigraphic forward modeling. The other is diagenetic forward modeling. And then we do the fracture forward modeling. Now, in stratigraphic forward modeling, what we do is we try to predict the formation and deposition of sedimentary rocks with time. So, for example, we have parameters such as subsidence rates or the deposition of fragments of rocks or production history of the different kind of grains which are deposited on time. Similarly, for diagenetic forward modeling, we try to model the chemical processes due to temperature and pressure, which alters the rock formation. And then you come to fracture forward modeling. This is where we are trying to predict the formation, nucleation, propagation of fractures. Now, these are different from the generally used statistical techniques because they are really all process-driven with physics-based approaches. So we are trying to use machine learning approaches for geological data gathering, data assimilation, and parameter derivation. And at the end, as you see in this iterative workflow, once we achieve these model results, we will incorporate them in our techno-economical assessment tool, where we will quantify the uncertainty and also present the potential geothermal potential estimations. Now, the main research consortium here, we are 12 partners, and we are various geological surveys from Denmark and Greenland, TNO, British Geological Survey, Geosphere Austria, and from Catalonia. We have several research institutions. Fraunhofer is the principal coordinator with Technical University of Denmark, University of Bari, and University of Vienna. And we also have from the application side 3 industry partners. SG is one of them, where I come from, where I work. And we have EVN and Risk Dialogue, which is actually the partner who are basically responsible for the social sciences aspect of the project. The different test sites, we have around 12 test sites, and these, as I said, they are different depositional environments. So we are trying to model in different data-rich areas. So we try to develop the models and calibrate using areas where we have a lot of data. That's why we have several data-rich areas, and you can see the sites are all over in Europe. And once we have the calibrated models, we are going to apply them in data poor areas, and these are also distributed all over in Europe. I'm not going through the details, but if there are any questions, any interest, I'd be happy to follow up later after the presentation. We'll have a talk by Florian Wellman later, so I will end with this. Thank you so much.
Thank you so much, Paramita, for the introduction of your projects and such interesting information. And last but not least, we have the GeoHeat project, which will be presented by Shakas Alexis. So please, Shakas, go ahead.
The intro is going to come from me. Alexis will then talk later. Yeah, thank you for organizing this webinar. I guess you see my screen. I'm going to talk about GeoHeat. GeoHeat stands for Georadar-Aided High-Resolution Exploration to Advance Deep Geothermal Energy Usage. And yeah, quite a word. You can also guess that the center of this project is some georadar. And as said, it's going to be me and Alexis from ETH Zurich talking today, and Christine from RWTH Aachen, of course, on behalf of the whole GeoHeat team. The GeoHeat project is coordinated by Eric Sanger from Fraunhofer IAG. The easiest to explain you the project in a nutshell is essentially this plot, this overview plot, and yeah, it has project risk and exploration costs on the 2 y-axis, and time, or yeah, essentially time on the x-axis. And I'm going to start with the first section, which we call this pre-drilling prospection. And here we start with existing data, and we start on a scale of around 100 kilometers. And yeah, we start with hundreds of possible sites. Yeah, so you already see the probabilistic nature of our approach. So yeah, we gather all the existing data and process it into a so-called LCOE heat map, which then reduces the possible sites further. In addition, in this pre-drilling prospection, we also call it low cost. We have passive seismic surveys included, and there is yeah, probabilistic framework involved here, and towards the end we then end up with one site after some geomechanical simulations. Christine will talk a bit more about this part later this afternoon. And yeah, we are now on the 10 kilometer scale, and we decided for one site, and then we drill. And here comes then the high resolution model, so the borehole model we call it, and here we then get a radar image of the subsurface, and we start to model the rock volume around the borehole, around 100 meters away from the borehole, up to 3 millimeters. This will also then allow us to optimize our drilling trajectory, maybe even redirect. Towards the end of this workflow, we then are able to combine all the different models and do this multi-scale integration and assess the whole reservoir long term. Here, Alexis and myself will talk a bit in more detail later this afternoon. The GeoHeat Consortium consists of 45 plus researchers, 6 universities, University of Pisa, University of Geneva, ETH Zurich, and Fraunhofer IEG, Delft, and RWTH Aachen from south to north, and then 5 companies as well, Guideline Geo, ALT. ALT is like an expert in borehole probes, and Guideline Geo is an expert in the radar technology. And yeah, then we have Boratec, Minio, Risk Analytics, and Seismics towards the end. And of course, the whole project is funded by the European Union and also supported by SERI. At the time, Switzerland had some difficulties with the Horizon Europe program. Yeah, and with this, I'm done with this intro.
Great. Thank you so much. Thank you so much, all colleagues, for brief projects presentations. So now we move into the general presentation sections. And the first one is focusing on innovation in seismic acquisition for urban geothermal exploration. And I would like to invite Mark Baker from Argent Projects to make a presentations. So please, Mark, the floor is yours.
Thank you. Thank you very much. Let me. Yeah. Okay. Okay. Yeah. So great. Wonderful to be able to present to you today on the innovation that we are working on as part of the Urgent project to create MEMS-based seismic receivers for urban geothermal exploration. Very quickly, InnoSeis Sensor Technologies is a spin-off from the National Institute for Subatomic Physics here in Amsterdam. And our goal is to commercialize some of the world-class research that is happening at the Institute, where it's most commonly known for its contributions to CERN and gravitational wave astronomy. I'm going to start with a very brief history of seismic recording equipment. I think everybody here is probably familiar with what seismic imaging is. And many of you probably more or less familiar with seismic recording equipment. I'd just like to point out that it's a very key element to seismic imaging because it forms a relatively large portion of the capital expense. Also, it's very a large driver for the operational expense of seismic imaging as well. And in these early stages of geothermal exploration, it's also kind of what the public sees as well. So it's also important for social acceptance, environmental footprint, and these kind of things. And as we're driving towards higher, we'd like to have higher resolution images, would like to do more geothermal energy, and geothermal is generally more budget constrained compared to other users of seismic imaging. So the equipment forms a really big component of how we can drive more adoption of seismic imaging for geothermal exploration and production. The industry has come a long way over the last few decades. So what used to be primarily geophone-based cabled systems, probably starting about 15 years ago, people decided doing away with the cables. And then we kind of had a period where we had solutions that were battery-powered geophones, basically. And that's replaced the cable problem with a pretty enormous battery problem. And then probably starting from about 10 years ago, we got the all-in-one geophone. So that was combining batteries and everything into a single device, and that was called a node. So receiver node, and this had huge implications on operational efficiency, also flexibility in terms of survey design, and it was a significant leap. So let's fast forward again a little bit further to today, where the current state of art is almost entirely nodal equipment. So these single point receivers, but they're still very limited in terms of being either high cost and bulky nodes, or where they are low cost, where you can get low cost equipment, then they're generally limited in the features that you would like to have. So the Urgent project really sets out to create a lightweight node that has a balanced feature set that is suitable for urban geothermal exploration. So, and kind of looking at what's out there now, you see a general trend that the more complicated, the more intelligent, the better the system is, the more features it has, it generally results in a more expensive and heavy product. So the first thing we did was, amongst the collaboration, amongst the consortium, we created a set of target specifications. So what does the ideal seismic receiver look like? Obviously, very important here is the data quality. So we need to have something that resembles or is better than the current state of art geophone. So those, for the technically inclined, the target specification that we're going for is 10 nanoG per root hertz. It also needs to be small and light. That's really driving the operational efficiency of a seismic image for a seismic crew during a survey. What we're targeting here is obviously it's got to be small, and it's got to be less than 300 grams, all up. So that's including the sensor, the battery, the enclosure, everything. Less than 300 grams is what we set out to achieve. It also needs to have wireless connectivity, and this is very much related to understanding the quality of the data that we're gathering. So every single device needs to be able to send back a message to the user saying that the data, what the quality of the data is, what the status of the node is, and so for both long range and short range communication. What also kind of factors in here a little bit, which is we had lots of interesting discussions about, is things like theft. So people steal nodes, or steal them either for malicious or non-malicious reasons, and you kind of want to know where they are. And so this also gives a way of kind of giving feedback in terms of I've been moved, and maybe if I have been moved, then where you can find me again if I was a node. And then finally, autonomy and ease of use. And so here, an important metric is how long does the device last on a single charge, and we're targeting at least 30 days. And ease of use, we're talking about things like just being able to deploy the sensor and then move on again, like we saw in the previous image. And also other things like, are we able to bury the nodes? Can we bury them under a little bit of soil so that they're even less obtrusive, really out of the way? But then if we do that, we want to be able to find them back again. So these kind of really interesting discussions we had. So I'm very proud to be able to present now the urgent node, which we have coined LEAF very recently. I don't think anyone else knows this yet, actually, but we called it LEAF, and it is based on our own MEMS accelerometer. And this really forms the core of the device because it's completely taken away the geophone, which is a relatively heavy, large and expensive part of a node, and replaced it with a MEMS accelerometer. So MEMS is a micro electrical mechanical system, and what it means is that we can basically create a geophone on a microchip scale. So something that used to be kind of this big is now something that can be on the tip of your finger. we were able to do this using we're using very unique and patented technology that we've taken out of the Institute. It allows us to create a mass spring system that is very sensitive while still being very small. So without going into too many details, that's very challenging to do, and we've been able to do that. So we've created a geophone on the microscale. So that's a very core part of the technology, but on top of that, also you need to have a number of other things. So we had to also obviously build a node around it. It has to have an enclosure that's robust and watertight. You have all the electronics too that can do the data recording, the storage, the timing synchronization, communication, battery charging, all of those kind of things. So that's really been a focus of our activities in the last 1.5 years. And I'll walk you through some of the considerations we had. So first of all, the enclosure. We wanted the enclosure to be something that was kind of uniquely identifiable as a seismic node, while also being, different from the rest. And then at the same time, it also needed to we had to be able to manufacture it, and it had to be kind of practical in use and all of those kind of things. So we went through a number of concepts and development phases, and finally ended up with a concept that we're very happy with. But then there was still a lot to do in terms of puzzling everything else together, because inside the node, then you have a whole lot of things. So we have we had to design the enclosure itself. It needed to obviously be watertight with a gasket. And then the electronics, we had to puzzle the electronics in there, redesign all of our prototyping electronics to fit inside the enclosure. The MEMS sensor itself, we also had to make some tweaks for this application.
Mark?
Yes?
Sorry, just quickly. We are still at this specification slide.
Oh, no way, really?
Yeah.
Oh, wow.
I think
okay.
you're frozen, because I also see you frozen in your image.
Oh, no. Okay. Okay. So size-wise, noise-wise, sound is okay. But
Yeah.
okay, that's weird. Let me
And I think everyone is curious to see the nodes.
Very much, yeah.
Maybe you can try to stop sharing and reshare again. Can you hear us, Mark? I mean, nobody's speaking, but okay.
Since we are waiting for the presentation, so please don't hesitate to ask your questions into the chat. Just a kindly reminder.
Okay, Mark has joined again. Okay, Mark, do you?
Hi.
Okay.
Is this better? Yeah.
Yeah, I mean, you're not sharing anything right now.
Okay. Yeah, no, I'll that's the next step, I guess.
Okay. Yeah. Okay, now we can see you move. So it's already better, yeah.
Okay, good.
Okay, great. Thank you.
Okay, so yeah, I'll try not to repeat myself too much. So you're saying I ended up on this slide here? Yeah. Okay. So okay, just imagine all the things I just mentioned again, but then with these images. Yeah, there's a picture of the node and the MEMS sensor. Here's a process of the the concepts for the enclosure, and then yeah, here I was talking about how we're putting everything together into the node. So the MEM sensor, and then yeah, I mentioned battery packs. Yeah, there's some antennas in there that have to go as well, and then a docking mechanism as well. Okay, so then yeah, so then we have so if you have a node, unfortunately that's not all there is. So a receiver system is more than just the node. There's a firmware that needs to be developed that runs on the device. We have a handheld application that can communicate with it. There's backend servers for doing the data handling, and then there's a harvesting and transcription interface, which is also all software. There's a docking station that has its own piece of embedded software, and also all of the quality control has to come through some kind of data handling and interface. So yeah, these are all elements that we've been working on extensively in the last year and a half. And then we were very happy to be able to do a field test at the end of last year, where we took a handful of sensors and did a small test in various configurations with the new eVibe from Seismic Mechatronics, which Jago will talk about in a few seconds. So we also have another larger field test scheduled for this week as well. And then looking towards the future, so our major goal is to participate with these nodes, demonstrate this technology in field trials in 3 different locations, which Jago will also talk a little bit more about. So we're in full swing manufacturing. We need to produce 700 of these devices over the next few weeks, and then obviously continuously testing. We're adding software features, getting feedback from the use of them in the field, and yeah, we're really excited about getting them into the field trials. So yeah, thank you all very much for your attention. I hope I've portrayed a little bit what it is like to produce a seismic recording system, and then hopefully in the future we'll be able to present some data, and in the longer term future, maybe on one of your projects you'll be using one of these nodes, one of our nodes. So.
Thank you very much, Mark, for such insightful presentation. And continuing with Argent, we now turn to a new electric seismic source developed specifically for urban settings. And our next speaker is Jaga van den Broek, who will present a new electric seismic source for urban geothermal exploration. So please, Jaga, go ahead.
Yes, thank you. Great. So short, I will give a short introduction. My name is Jaga van den Broek. I work at Seismic Mechatronics, and yeah, I will tell you something about the new electric eVibe today. So who are we? Seismic Mechatronics was founded approximately 10 years ago. It was also a spin-off. We had a spin-off from the Delft University of Technologies. I believe they're also here today. So our main role is to develop and manufacture the new 20 kilonewtons eVibe. I will tell more about that soon. And you might have seen us under another name, Faraday Geophysics, and that's the name we use to operate worldwide with the services we provide, and we do that with the eVibe. And in the Netherlands, we do a lot of geothermal projects. So yeah, that aligns very well with Urgent. So the goals for Seismic, as I said, design, manufacture and test the new innovative eVibe source together with InnoSeis, technical readiness level 5, or maybe more, we will see. Our system needs to be able to generate repeatable and low distortion acoustic signals over a broad frequency range. The target depth is around 4,000 meters for one of the test sites. I will tell more about that later. And then obviously we want to have sustainable low impact seismic acquisition in urban and industrial areas. And also very important that we will make sure the system delivers high quality data collection while still reducing acquisition costs, because we also want to make better business cases for geothermal drilling. Here you see an overview from the systems that we have. So we're building on proven performance already. So around 10 years ago, we started with the Lightning eVibe, which is a 1.7 kilonewton source. It's much smaller. It's about 100 kilograms, so that's quite small. Then we developed the Syncro eVibe, which is a 2.4 kilonewton vibe. After that, the Storm eVibe, which is a 10 kilonewton vibe. And then now for urgent, we are developing the 20 kilonewton vibe. I'm not going into too much technical detail, but the eVibe, they are built on the performance of direct drive motors, which makes almost frictionless movement, and that's also the reason that we are able to produce highly repeatable signals, and also with very low harmonic distortion. So we can still deliver with our, in terms, if you look at conventional vibes, we have much smaller vibes, but we can still deliver high data quality. Also, our system enables low environmental impacts. We have minimal emissions, we have no hydraulics. As I said, the eVibe is electric, battery powered, clean, and also quiet. Also quite compact, mobile. It's carrier agnostic, so we can use a various range, which is also good for operational flexibility. You can use electric carriers if you want. We have a broadband frequency range. So that are the merits that we have with our system. I have here a few pictures and here a small video of the Storm eVibe in the urban and industrial areas. It's not the hurricane yet, but then you can get an idea how it looks like. As you can see, the system is very compact, and the operations require only a very small crew. Depending on the location, we might use additional personnel for traffic control, but all in all, it's only a very small crew we need. These are also important to notice. These are all shot during the evening and night. That's how we work. These are shot in the summer, so that's why you see significant daylight still. But this is also a major advantage also for the residents, because most of the time we hope they don't even know that we were there, because we place the notes, mark notes during the day, and then we shoot during the night. Here you see the system we developed. Just a short overview. Here you see the eVibe unit itself. That's here in the total design. In red, you see the electronic cabinets. Yellow are the batteries. This is just for tools. The software we also develop in-house. And in the end, for the urgent project, we decided to mount it onto a trailer, but we could use other carriers as well. We decided to go with a trailer because it gives operational flexibility. It's easier to transport and it's also quite easy to use various carriers. In addition to this, we're also working on a alternative frame for a telehandler that might be a little bit more useful for small residential streets where you cannot, where it's really small and it's really hard to maneuver. It depends. It both has its merits and demerits. Here I have a small video that was taken during the first test with InnoSize that Mark told you about. So please put your sound so I can, you get an idea how it sounds, and it's very low noise. You hear it? Yeah, that was the sound that our system makes. So that's also a very good advantage that we have for for in cities. Yes, I need to add, this is a pretty big tractor, but we can use a much smaller one. So we will start in a month with one of the first tests, which will take place in Hungary. That will be a 2D seismic survey. The target depth will be 1,300 meters, so that's the shallowest target. After that, we will go to Poland. This will also be 2D seismic survey with 2,700 meters target depth. And then in the end, we will go to Belgium, to the Balmat site. This will be the deepest targets, approximately 3.5 to 4,000 meters, and this will be a 2.5D seismic survey. So we're very enthusiastic, and let's see what the tests bring. So thank you.
Thank you very much, Jaga, for such interesting presentation. So we are excited to get the results of your survey in the upcoming future. So following our agenda, we switch to FindHeat project. And I would like to invite colleagues from the project, the Pierre-Oliver Bruna and Alexandros Danielidis, to present an innovative exploration philosophy and toolkit for finding geothermal heat efficiency and sustainability. So, colleagues, the floor is yours. I guess you're muted.
Can you hear me now?
Yes. Good.
Yes, sorry. So we try to do this in one room.
Some echo.
Yeah, you need to mute one of the two, otherwise.
Yeah. I'm muted. And the volume. Yeah. Okay. This should work.
Sorry, you have to to mute the other computer in terms of audio. So if you have two computers, one of them should be without audio at all.
Is it working? Do you hear us now?
Yes, but
Sorry for that. Yep. So I'll start and then switch to Pierre, and then we'll come back to me. We're sitting in the same room. Sorry for the mix of the two computers. I was mentioning that as Pierre mentioned in the introductory presentation, one of the issues that we face is that we have economic and technical risks and negative public perception at times, geological uncertainty, and all these result to success rates below 50%. And what we aim to do in FindHeat is to develop fast and low-cost software and exploration tools, be able to perform robust economic assessment that is seamlessly connected to the geological modeling, have trusted communication across partners, and also to develop training for technical and non-technical experts alike. We do this in a number of cases. We'll see some examples in the presentation today, and we hope that we're able to deliver on inherently lower technical and economic risks for geothermal projects. The research questions that motivate us are, firstly, how do we quantify the impact of geological uncertainties during exploration and appraisal? So we will look at two examples here for the Delft Sandstone and Ritter Softman. These are the first ones that we've started working on. And future research will be outlined for the Sherwood Sandstone, Ritter Marietje, and the low entropy Iceland fields. The next part is how do we quantify the value of information based on relevant techno-economic indicators? And for that, one of the things that we are developing is a unified techno-economic framework for heating and electricity production using probability that allows us to have some key performance metrics on which to do this assessment. And further on, we perform global sensitivity analysis to be able to rank the importance of uncertainties to these performance indicators. And the last thing is how do we communicate the research insights related to uncertainty and value of information to both technical and non-technical stakeholders at the end of the project, which leads us to the FindHeat tool. Some nomenclature that we have tried to unify within the project, and we present to you here for clarity, has to do with how we deal with all these case studies. So we first start with the geothermal play type, which is defined by the heat, fluid, and permeability triangle. From that, we move onto the conceptual model that is based on the specific case studies that we have in 6 different locations. And then we have scenarios that are members of the conceptual models that might have different representations of features in those conceptual models. And lastly, we go to realizations that describe geological realizations based on heterogeneities and rock properties and other parameters that we are using to parameterize these models in the scenarios. So how can we quantify the impact of geological uncertainties during exploration and appraisal? I give it to Pierre.
Yeah, so for this part, we will present you 2 case studies. So the first one is the TU Delft campus. For those who are not aware about this case study, so it's a geothermal project that that was recently achieved in the campus of the Delft University of Technology. So we are reaching with that project the depth of 2.2 kilometer, and we target the Delft Sandstone, which is a sedimentary aquifer at depth. So this project is really cool because it has twofold. The first part is an economic outcome. It's going to be used to heat up the campus and also part of the city of Delft. And the second aspect is that we retrieve with that well a lot of information, a lot of geological and geophysical information in terms of core, in terms of logs, in terms of surveying, geophysical surveying around the well. And this is a very cool picture of the rig when it was installed on the campus, and we had the chance to visit the site and to see how it works basically. So what are we talking about? We're talking about the Delft Sandstone. So we are in the West Netherlands Basin. So this area around there. This is The Hague. This is Rotterdam. And this map from ThermoGIS show you the potential, the geothermal potential of this area, which has a high potential highlighted in green here. What is the Delft Sandstone? So the Delft Sandstone is composed of 4 different members. You have the lower Albacedam member at the bottom of the series, which is composed of braided river. The upper Albacedam member composed of meandering rivers. the Delft sandstone member, that is a fluvial plain, coastal plain, and on top of that you have the rhodorized claystone member, which is sealing the whole system. With this, those cartoons, basically we define the plate type, which is a sedimentary aquifer. If we go a bit further into the detail, what we are interested in is the Delft sandstone, which is a fluvial deltaic environment. And this fluvial deltaic environment is our conceptual model. Has a lot of heterogeneity, depending a bit where you are located into that system. If you are more distal or more proximal, the geology of the system will change a lot. And what we want to do is to actually try to investigate what is the impact of this change of geological environment onto the performance of the system. So we created two scenarios. One is located in the lower delta plane, and the other one is in the upper data plane. And we started to investigate a bit what are the uncertainty of those two systems. And this is the work of Esther Claridge. So she's a PhD candidate at TU Delft. She worked a lot during the first year of the project on trying to define a number of architectural elements of this lower coastal plain and upper coastal plain. And she identified, for instance, the sand body ratio, the sinuosity, the frequency, gradation, and flow direction. And she made a design of experiment with n members value to actually assess the system. And to actually test those different scenarios, she used a software called RRM, which is stands for Rapid Reservoir Modeling. So this is a software that allows you to build in a very limited time a series of conceptual realizations of a certain geological system. It's very agile. It can do that very quickly, and you can add more and more parameters when you need it. So those are some of the realization that Esther did during her first year of the PhD, and those are not meant to be exactly what is going on the subsurface, but they are meant to test some possible situation and some possible architectural element, combination of architectural element in the subsurface. So the initial result are in terms of simulations, or based on those static model. We test the progression of the cold plume, and this is an animation made on DARTS, our in-house software for flow simulation. And this configuration is for the contacted model, and test the configuration where the producer and the injector are perpendicular to the flow direction, to the paleo flow direction of those channels. And basically, what we get in terms of lifetime of the system is quite different. So for we have the three model presented here, and for the contacted, the blue model, and the embedded model, we have a very different lifetime, being 35 years for the embedded model and 43 for the contacted model. Now, Esther tried also another configuration of the doublet placement, and now she placed it parallel to the paleo flow direction, and the picture has changed a lot. So now the contacted and embedded model of a quite similar lifetime. They are still different, and they are flipped. So now the contacted model has a smaller lifetime than the embedded model. The second case we are studying is the Rittershofen case. So Rittershofen is located in the Upper Rhine Graben,
It's this location, which is not that far away from Strasbourg, if you want to picture a bit. In that location, there are two sites targeting the fractured basement, the granite at depth. So this is a picture of the Richterhofen case. So we define the plate type, which is the basement. And if we look at the cross section of one of the well in Richterhofen, you see that the doublet and the open hole section of those doublets is located into the Bunsenstein, so the Triassic sand, and also in the basement. What you see in red in that picture is a fault that is really close to the two wells, and this is why we define the conceptual model as a faulted geothermal system or geothermal reservoir. So this is the work of Valeria Nogales Herrera. She is also a PhD candidate at TU Delft. She started at the same time as Esther, and she did basically the same exercise, but this time turned towards the fault characterization. And for the fault characterization, she defined two main elements: the geometry of the fault in terms of the geometry or the architecture of the damage zone, and the geometry of the fault trace. And she defines also some petrophysical parameters of the damage zone and of the rock surrounding the damage zone of the fault. So that's this table is the main input for generating the scenarios. So you have here two scenarios. The gray part at the bottom is the basement. The colored part represent the different units within the Bunsenstein, and the upper yellow part is the cover, is the sedimentary cover. And if you see, it's a bit difficult to see, but you have the trace of the fault, and aside from the fault, you have a damage zone, which is here symmetrical on both the hanging wall and the footwall. And here it becomes very asymmetric in the hanging wall compared to the footwall. And based on that, she realized a series of 12 different RRM models. And one of those is presented here, where you have the fault with a certain tortuosity and a damage zone that is here symmetrical and represented by this series of cells in the model. The initial result of this part are the following. So here you see different model selected. The red model are for the tortuous fault and asymmetric damage zone, and the blue model are more for a straight fault and a more symmetric damage zone. And you see that the lifetime of the system is in this case quite different. So the blue models tend to have a lifetime of about 10 years or less, and the other model have a much higher lifetime. So those are the first result of Esther and Valeria. So in the Netherlands, the well connectivity to communicate with somebody is a key. So the connectivity is defined by the sand body frequency and the sinusoidity plus the vertical connectivity between the different sand bodies. The well placement relative to paleoflow has the greatest impact in the system lifetime. The doublet parallel to paleoflow have decreased the system lifetime and economic performance. And the effect of aggradation is highest in the system that are perpendicular to the paleoflow. For the Richterhofen case, we presented a three-dimensional volumetric deformation zone in the fault that include the damage zone and associated permeability. Variation in the fault zone geometry are first-order control in thermal breakthrough. Tortuous fault trace tend to delay the breakthrough relative to linear trace, and increasing fault damage zone asymmetry correlate with later breakthrough time in the model. For the coming years, we are targeting additional case studies. So Esther is going to go in the UK to see the Sherwood sandstone, which is pictured here. So it's a fractured sandstone, and we will have time in the field to describe those system. And Valeria is going to work on the volcanics of Reykjavik, which we visited during the last consortium meeting. So that's a picture of one of the installation targeting those reservoirs. And in between, we have a master student working in Czech Republic in Litomerice on the deep metamorphic basin. And on this, I pass on to Alex for the next part.
Yeah, so the question then becomes how we can define this value of information and what are the relevant techno-economic indicators for this. This is a typical subsurface project cost curve where you have a very high uncertainty, low bankability in the beginning, and as you progress in your pre-survey exploration, testing, etc., your cost increase and the risk decreases. And if you have a successful project, then you end up with a low risk and an operational project at the end. And the idea for us is to be able to do good predictions, so we always end up with projects that are inherently low risk and high success rate. And just to identify here, what do we consider in system boundaries in this system? Just a very high level order of what is included in this economic assessment. So if you have the broad overview of a geothermal power plant, the distribution network, and the final users, whether we talk about heat or power in this case, it's not really relevant. But what we do consider is the subsurface characterization, like Pierre was just showing with multiple models. And then on that, we have some development choices that have to do with the well numbers, provisions, and controls. And finally, we have dynamic responses of that system in terms of pressure, temperature, in time. So this is the part that we include in our analysis, and allows us to derive some economic performance metrics like a levelized cost of heat or energy or electricity, net present value, expected monetary value, and some others, for example, like the extent of the cold plume or the heat in place recovery factor. So this we assess with a probabilistic techno-economic simulation. I show an example here from some previous work that we've done on the storage systems, where we can continuously and at arbitrary time steps assess the performance of a system like this. You see here on the left-hand side, the pumping power, produced net power, generated income, and the corresponding cash flow. Bottom left is the net present value, and bottom right is the levelized cost of energy for a 15-year project in this case. And on the top right, you can also see how we assess this in terms of the probability to run multiple realizations. So in this project, we're going to expand on this previous work and be able to integrate also the electricity production, but also this probability in terms of across the range of all the inputs. So we could consider changing discount rates in time, changing heat price in time, electricity prices, and so on. And that allows us to also be able to assess the Monte Carlo convergence of the techno-economic indicators, which we will then use as the VOI metrics. This is the work in progress. So just to give an idea of how this might look, on the top left hand side, you see how this global sensitivity analysis looks like for a direct use geothermal system, where we identify, for instance, in this example, and this is not directly connected to what Claire was showing earlier, the net gross, the power burn, and the correlation width as most dominating the production oil temperature. Whereas for the injection well BHP, it's basically the porous permeability, the net gross that define this, where all other parameters tested in this example have relatively low importance. So by doing this kind of exercise for different performance metrics, we are able to identify the most influential ones. And what you see that then we can later translate this into what you see in the bottom right, which is the distributions of net present value with this example models. And we see that in some cases, for example, the pore permeabilizations in that case were not so much changing the behavior of NPV, whereas the salinity we used to model the fluid did result in changes, and so did the injection temperature. So moving towards impact, so now we're looking a bit more towards work to come, but we try to paint the picture already for you. We want to have this toolkit for technical and non-technical stakeholders at the end of the project, and that will cover several different aspects. The first one is the public engagement, where we discuss going from geological concepts and models to actual societal perceptions. So the first part of this work is already completed, and it looks at the literature review of the local culture and how people in certain localities and certain geothermal settings perceive and understand risks and benefits associated with geothermal energy. This will be followed up by a cross-country survey where we looked at not only the local culture, but also other factors to identify the perceptions towards a geothermal project, and be able to derive a cultural analysis instrument to see what is the cultural awareness in terms of geothermal energy. Based on this, we can build localized engagement strategies for local communities and to have material and focus groups developed for the specific geothermal play type. Realizing the results is bringing all of this together in the FindHeat toolkit that incorporates initial and acquired knowledge and modeling and proposes guidelines for geothermal explorations, and also connects to the social science studies using scientific results to have better adapted solutions to engage with the public and deciding authorities based on the context. So you can see here an example of case worked out in the top half of the image where we start with a prior model. We have our standard data. We have some uncertainty factors like the ones that Pierre was discussing earlier from the work of Esther and Valea. Based on the design of experiments, we're able to generate an ensemble of models using rapid reservoir modeling and simulation tools like DARTS and CSMP++, depending on the enthalpy level. That gives us then our performance indicators, and that can already be a decision support framework to show us what is the uncertainty range across all of these indicators. And then if we introduce now the non-standard data, so SWR, drone images of web AVO, or electromagnetics, what we can do then to reduce these uncertain factors, for instance, to better constrain the flow trace geometry or the presence and characteristics of background fractures. And we run again through the same workflow, then we are able to reduce the range of uncertainty. And then this differential between our initial state and what we are now able to produce with these exploration methods allows us to quantify the level of improvement in terms of technical performance, but also the value of additional information added. That's in a nutshell the overview of the project. It should lead us to optimize exploration and reduce risk, a suggestion for best practice of exploration workflows, and all of these are exemplified in this modular FindHeat toolkit where worked out examples can be found for each of the geothermal plate types, and end users can also use their own data to run through the same tool. I'd like to thank you for your attention, reminding you again our partners here, and I'm happy together with Pierre to answer any questions you might have. Thank you.
Thank you very much for such excellent work and for sharing the case study and initial simulation results with us. So let's move on, and the next presentation is about 3D geological modeling, sensitivity analysis, and uncertainty quantification. And Florian Wellman from Go Forward project will present the key results. Please, Florian, go ahead.
Thank you. Can you see my slides already? Did this work?
Yes.
Okay.
Yes.
And just a quick question, because we are running a bit late in the agenda. If I take the 25 minutes, that would be until after the coffee break. Is there any adjustment, or should I just go on?
You can just go on. We still have 10 minutes before coffee break.
Yeah, okay. Good. So yes, it's a pleasure, first of all, to be here and present a bit on behalf of the work that we are doing in the Go Forward project. And I have to say it's a bit of a different type of presentation here. I focus a bit more on some of the methods we are also using in Go Forward and also in the GeoHeat project, which will then be introduced a bit later by Christine. But I would like to present a bit the methods that are currently being developed in the field of 3D geological modeling and how they can be used for uncertainty quantification and sensitivity analysis. So this is a very broad view here, but what we typically look at are some structures in the underground. And of course, this is now not below ground, which could be a geothermal reservoir, but something above ground in the Pyrenees. And what we see, of course, in reality is this high complexity of structures in all kinds of scales. You see maybe here some carbonate layers, some clay, sandstones, and so on. And then what we do in practice is we limit this down to actually this high complexity in 3D, we limit down to lines in 2D, lines in 2D or interfaces and well, 2D manifolds in a 3D space. And I think it's important to reflect a bit on why we do that and to bring us to the next step. And this is, of course, because this is where things changed, right? We had a long, long history of mountain building, of sedimentation, deposition, and so on. And finally, tectonic processes, which led to fracturing, faulting, and so on, overprinting, diagenesis, until we get to the state that we see today. And a lot of what is happening, of what is relevant to us, happened at these basically, small instances in time, which we now see as 2D manifolds in 3D space. In the Go Forward project, we're looking at many of these aspects from the simulation point of view, stratigraphic forward modeling, fracture development and propagation to a certain degree, or representations of fractures in 3D. And what I'm going to talk about here is this element of geometry, so of these basically 2D manifolds in 3D space. And this is one of the combining elements, I would argue, in geology that we use in many applications. The question is basically, how do we obtain these representations of potentially highly complex elements in 3D space? And to start this question, actually, we're going to get, from instead of looking at a 2D image in 3D space, even simpler to look at a circle, so a line in a 1D line in a 2D space. And the question, how do we actually draw a circle? How can we describe a circle with mathematical functions? And the first thing we need is, of course, we need some form of a coordinate system to describe what we see. And then we have multiple ways to represent the circle. One commonly used one could be a so-called parametric method, where we have one parameter t, and we describe the circle basically based on trigonometric functions on this plane. We see here by changing t, we can kind of draw out the shape of the circle. There's another very common representation, which I'm sure when would have asked you the question, how do you describe a circle mathematically, the first thing that comes to mind to many people is the so-called circle equation, which basically is the definition of a field or a set in the end of x and y points, which fulfill this equation on the top right side here. But what this actually means is that we define a 2D field, and one contour in this 2D field happens to be the circle. So we could also represent this as a 2D field drawn here with x squared and y squared values. And we see where this 2D field happens to have a value of r squared. This is where we draw basically our circle. So in some sense, we define a field and we extract a contour from this field, and this contour, happens to be the line we're looking for, the circle. And in this view, you can actually see this also in a sense, as a shape in 3D, right? We can see this as this bowl-shaped, basically drawing out here the r squared and y squared shape, and where we intersect this shape with another shape, which happens to be here simply the xy plane. This is where we basically get our circle. And you can see from this representation here, from this view, when we shift the contour level up and down, we get to different shapes of this circle. So this is a very simple representation, and you can think, okay, what does this have to do with geology and geothermal exploration, especially here today? Well, oh, there's one more way. Sorry, we could also say that we draw out the shape of the circle with piecewise linear interpolation, basically by adding points, more and more points on the circle, and we say in between those points, we simply have our geometry here, the circle. Now, all of these methods have somewhat equivalent ways to draw shapes also in 3D. The two main differences are that for these parametric surfaces or lines, then the parametric way to describe the circle, once you put in a value for t, you get out a point on the circle. For these so-called implicit representations, it's more difficult to find a point on the curve because you do have to do a contouring, but it's actually easy to determine if you're inside or outside of this curve. And as you saw as well, we can actually get circles which are in this case concentric by extracting interface or lines from different contour levels. And similar things and ideas we can use in 3D space for the representation of geometry and in geological models. So there are many ways which use these so-called parametric methods. One are these non-uniform rational B-splines, NURBS methods. And there are also many of these so-called implicit representations. And with all this introduction here, what I want to point out is there are many ways to represent geometries. They all have advantages and disadvantages. One of the advantages of these implicit field representations is that you can represent multiple geological sequences or interfaces, stratigraphic sequences, for example, with one of these fields, one of these scalar fields, and then extract iso planes basically from this field as multiple geological interfaces. And this is, again, leave a bit maybe some of the details out here. Let's move forward in the interest of time. There are many ways to do that. I'm going to talk mostly about one of which can be considered a meshless interpolation based on geostatistical functions. And I'll show hopefully a bit, to you how we can use these to construct also shapes for geothermal exploration and how we can link these then to uncertainty quantification and sensitivity analysis. Actually, in the interest of time, I'm going to leave the nice slides with equations out. Let me move directly to an advantage of these methods, of these of these representations as ISO fields. One point I would like to mention here is that they give us quite a high flexibility and a lot of power to represent shapes in 3D. This includes not only things like overturned features like dome structures and overturned folds and so on, but they are also very flexible. And that's what I'd like to show with this little example here. You can see in this image, we have two interface points, which could be interfaces of a geological, say, or of a geothermal reservoir, for example, or some layer of interest. And we have orientation value, which may be measured somewhere in an outcrop, or maybe also from a well somewhere, or even just something which we extract from a seismic image. If we would have this information and say, let's draw a geological interface, given this information, it would probably look like something like this, right? We have an interface going through these 2 points, and we have somewhere in the distance here, we would assume that we have, based on the shape, on this deformed shape, that we would measure an orientation like that. Now, if we would change only one value here, and so we only change the orientation and say, we assume that we have a different measured orientation somewhere else, you see that, geologically, a reasonable assumption could be to say that we now have these 2 points, so our interface follows the points, but then it has to bend up again to match to the orientation value. And this is also what these methods give us, because we always interpolate this basically a field, and we can take the gradient of this field as an orientation in 3D space. Point here is, without taking this a lot further, that these methods give us a lot of flexibility in representing interfaces in full 3D space. And in the end, when we define at least the cross covariances in this case correctly, they give us a good relationship between different types of input information that we have. Now, all of this together, this is allowing us to construct these models in 3D space. And one thing that I would like to highlight here is that, when you use methods like Petrel for geological modeling from seismic data, or many of the other methods which are out there, usually you end up with a lot of input points to represent your geometry, the geological interfaces in 3D space. But it's actually quite straightforward to construct reasonably complex, at least 3D geometric representations with a small number of input points. Mathematically speaking, this means we can represent these shapes with low-dimensional geometric parametrizations, and this gives us quite a lot of possibility to include them in uncertainty quantification workflows that I'm showing in the following. Up to now, I only showed you these fairly straightforward, simple interfaces, or maybe stacked and then folded in a similar way. So this is arguably quite simple geometric settings. To get to more complex geological models, what we do is then we combine multiple of these fields, and then we define intersections between them. And in this way, we can construct typical complex geological models. One of these methods also implemented in the open source package GemPy. So this is a small plug here for one of the developments we've been doing over the last years. So a lot of this is accessible as open source tool if you at least know some programming, because you need to develop the models. There's no nice GUI interface. It's GUI. It's really based on Python scripting, but at least it gives you quite a lot of flexibility to integrate these methods in modeling frameworks. And then we get these models. So this is one of the models from our using this modeling software here for the geothermal site in Weisweiler project near Aachen. So you can see on the left the city of Aachen still on this on the satellite image. And this is what the geometry could look like below the in the subsurface, as much as we know at the moment. Maybe some of you know that we have a big campaign for seismic campaign happening right now in the area to determine the interfaces a bit better, but to the geometry of the subsurface better. This is our current state, but then of course always the question is, as we heard also in the last talks, that there's always a high degree of uncertainty about these representations. And just to point this out here, different to what we've seen in the last presentation here, we don't look at the, for example, channel structures inside one of these reservoirs, but we look at the general geometry of the sedimentary layers and faults. And so this is, leaving now a lot of the technical details out here, but based on these low dimensional parametrizations, we can take these models and implement them in uncertainty quantification workflows, which means, as here shown very schematically with this movie on the right side, that we can change points, input points, and we get an idea about the expected variability of the geometry in 3D space. Now, this is one point. It's nice to have something where we have forward models, where we have some quantification of uncertainty. But in practice, we have a lot of additional information that we also collect in many of our projects seen here. And then the question becomes, how do we reduce uncertainty with additional information? And to introduce this part of it, let me just show you one, again, very simple example. Let's assume, we have here an estimate in 1D, so at one position somewhere in space about the position of an interface at depth. We have here, blue interface and green, and between there we have some maybe our geothermal reservoir. Now on the left side, you see a PDE, so a probability distribution about our expectation of where we would intersect this reservoir if we were to drill at this location. And if we now draw samples randomly, so we generate multiple possible reservoir positions. Basically, you can see here on the right-hand side, these are, what we see in the movie is the type of reservoirs that we could obtain. Now, we may have additional information in this region. For example, quite often we know that we have some expected thickness of reservoirs based on information maybe in the vicinity or geological considerations of the general depositional setting and so on. So what we can do is we take the range of initial geometries and we try to at least match this information of the layer thickness to obtain what is then called a posterior distribution. So for those of you familiar with inverse theory, this is a probabilistic workflow and a version. And now we see that we basically still have uncertainty maybe in the position of this reservoir, but you can see that the thicknesses that we obtain now, they are more or less, well, they are similar, and to be more precise, they actually follow exactly this expected layer thickness that we provided as a so-called likelihood function. So this is very powerful. It allows us to combine elements of uncertainty in geometric models and combine them with additional information, for example, from geophysical measurements. And this is one example I'd like to show you very quickly. So what we can do is we can combine then these geometric representations with forward models of gravity, for example. And in a similar sense, now you see here these input points at the base, and this is actually a full 3D model. And at the top, we see the expected the gravity signal that we would measure if this would be the truth. Yeah? And so we can use this information then in inverse frameworks to combine this with actual measurements of, in this case, for example, gravity. And Christine will show in the presentation after our lunch, the coffee break, if we still have it, how this can be used for other types of geophysical information. And now, again, maybe looking a bit at the time, let me move forward just a little bit to show you some developments in this field currently that I think are of interest because they link to a lot of potential. And one of them is, of course, that also machine learning methods have been entering this field in the last, say, 10 years or so. And sorry, one of them is using machine learning methods to obtain these representations more efficiently in so-called implicit neural representations. So in senses maybe similar to what you know from forward simulations, you can emulate part of the geological modeling process with neural networks. And in these cases, these are coordinate-aware neural networks, which allow us then to generate these scalar fields from which we extract the surfaces in actually very efficient ways. And how efficient is actually quite stunning, I think. So this is a work from a colleague from Canada who generated a model for 2 provinces of Canada. So this is basically the size, I think, yeah, approximately twice the area of Germany, the surface area of Germany, with 6 million constraints, so 6 million input points and orientation values in approximately 1 hour. Quite stunning. So, I mean, this is now not a low dimensional parametrization anymore, but I think it's just to show a bit in which direction these methods are developing. Okay, let me move forward a bit more quickly now, again, just to see, we save maybe some time. Oh no, let me show you maybe this example here. Also possible is to integrate these modeling methods more efficiently also in modeling workflows. And this is where we have a lot of links to the EU projects presented here. So quite often what we need to do is, of course, we have the geological models, the structural representations. Then we need to parameterize reservoirs, for example, with permeability or porosity, for then process simulations. And in the end, we have always the step of visualization and analysis of the models. And we work in some projects, one of them here, one of our PhD students, on combining all of these steps with so-called domain-specific languages, which enable you then to take some of these modeling methods and replace them with others. And then see what would be the effect on the subsequent process simulation and, for example, the geothermal prediction. One more point, because I talked about, we had this in the title, so at least let me mention this briefly here. Because we have all these components linked from initial input to output, As I showed you a bit, we can use modern machine learning frameworks like PyTorch, JAX, TensorFlow, and so on, and use the capabilities of automatic differentiation in those frameworks to basically obtain geological modeling with a direct analysis of sensitivities. And what this means is, I've shown this here at the bottom left with a simple example for a radial basis function. But if you were to make a prediction at this dashed line here, so at point 3, of where we would obtain our interface, you get directly the sensitivity to this output point, to this prediction, basically, of all the input information that you used. And this can scale, this scales to hundreds or thousands of input points. And this is very powerful because in the end, it tells you how all the parameters that you have in your model influence your output. And we've seen the talk before was about value of information as well. In this case here, this is of course based on information that we have in the model, but it's giving us directly the sensitivity, and you can basically go, based on the analysis, if I were to drill at this location, how much does each point in my model influence my prediction? It gives you a handle to see which of the points matter and where you want to be rather sure, and maybe which don't matter at all. And if you're uncertain, it also doesn't matter in this case. Okay, how does this, and this scales also to a forward modeling of geophysics and so on, but that's just a small side note. So how does this all enter into Go Forward? In our Go Forward workflow, Paramita showed this in the overview at the beginning a bit. We have multiple components linking different tools together, from basin modeling to these diagenesis, geological modeling, petrel, or extraction of points, and these forward simulations and techno-economical assessments. And in many of those, actually, geometric elements enter, especially in stratigraphic simulations, these 3D reservoir models and techno-economic analyses. And based on the methods I showed you here, we can actually use some of this power to get to also probabilistic assessments in uncertainties in this workflow. And as I mentioned, Christine will also talk about this in the GeoHeat presentation, following directly afterwards, and where we basically also link these geometric modeling methods into process simulations and combine them with passive seismics for a reduction of uncertainty. Okay, so just some final thoughts here, and always points to discuss, but one, I think, important point I wanted to show you here is that geological modeling, as you may know it also from some software tools, should really be less seen as a fancy visualization method of our thoughts in 3D, but really a scientific tool which enables you to test hypotheses, to look at sensitivities, at uncertainties, and so on. And I think it's important also to mention this point. It's not really about the software that we are using for these methods, like some people use Petrel, others GoCut or whatever. It's really about the underlying algorithms, like in any simulation framework that we are using. Wanted to mention also there's a hugely, rapidly expanding open source ecosystem of enabling these methods, also without partly expensive commercial tools, of course, at convenience, not the convenience that you have, but at least in terms of the methods that are there. Still difficult to keep those active. This is why projects like Go Forward and GeoHeat are excellent, because they allow us to develop these methods further as open source tools. And one last thing just to mention, of course, also AI is entering in this field on many different aspects, machine learning components, but also large language model based tools. So let's see where this ends in the future. Definitely an exciting time to work on these topics and to integrate them, of course, in geothermal workflows. And that's it. So thanks to the organizers of the webinar. Thanks for getting all this insight from different fields, and to the attention and taking the coffee break as well. So thanks for listening. And of course, here, happy to answer questions in the chat, I guess.
Yes, thank you very much, Florian, for sharing these insights regarding methods and 3D geological models. So we are behind schedule in 15 minutes, so we will need to move quickly to the next segment, and we suggest to take maybe 5 minutes coffee break and back in 4:35, I guess, to run according agenda. Would it be okay? Okay, then let's please stay connected, and we will resume promptly with further 5 presentations.
Thank you very
5
much.
minutes.
See you soon.
Thank you. So, dear participants, dear speakers, welcome back. So let's continue with GeoHeat project, starting with methods that link regional screening and reservoir scale assessment. And I would kindly invite Christian Roper from GeoHeat to make a presentation.
Yeah, thank you. Try to share. Can you hear me and see my screen?
Yes.
Yes, yes, thank you.
Okay. Okay. Yeah, I will today present the GeoHeat exploration chain from the regional scale to the reservoir scale, in which we want to explore low-cost and probabilistic exploration methods. I'm Christine Bober. I'm working at RWTH Aachen, and there we do lead the GeoHeat work package that is dedicated to this exploration phase. Okay, so here again, the project workflow that you have seen already before in Linus' presentation. And in this presentation, we focus on this very first part, on the low-cost pre-drilling exploration, covering everything from regional scale up to the reservoir scale, where we then end up with a borehole placement strategy in the end. Okay, so here's the overview of our GeoHeat work package. The workflow starts with the LCOE analysis on regional scale to identify areas favorable for deep geothermal projects, and a more detailed investigation then on the reservoir scale, where we continue in parallel with passive seismic methods, measurements and inversion, and also with the structural geological modeling, as Florian just presented in his previous presentation. And in both cases, we use stochastic approaches, and therefore probabilistic subsurface models are delivered from both approaches here. And we aim to then combine results from both approaches in this joint structure probabilistic model, for which we apply a data assimilation strategy to the structural model to assimilate additional information such as the inversion results. More on this then later. And then we have all available information in this joint model in an interpretable manner. And then using numerous realizations of this joint model, we hand them over for geomechanical simulation that can be performed to finally point to an optimal borehole location for additional investigations on the borehole scale that will be explained subsequently by Alexis. Yeah, and results from all the steps can then be used to update our LCOE map that I will present in more detail now. Yes, so this LCOE analysis, levelized cost of electricity, it ensures that all the subsequent exploration steps focus only on economically meaningful target areas. And we continue only where we have a suitable LCOE, and the site location, the location selection is not only driven by geological suitability. To do so, we use a so-called meter model for estimating the electricity price using a geothermal energy model. And we apply this to our joint case study in the canton of Thurgau. That's what we call the regional scale. Here you see the boundary of Canton Thurgau and model input analyzed for each location in Thurgau. Here, for example, the distance to the next major transmission lines. But the analysis integrates more parameters such as subsurface temperature and depth, drilling costs, infrastructure costs, heat demand, and risks from induced seismicity. The analysis results in several maps. Here in the top row, you see the temperature gradient, but you also see the corresponding LCOE maps with and without heat credit, where warmer colors correspond to a more competitive cost. And in the bottom row, you see LCOE maps as well that reflect possible additional costs relating to seismic risk mitigation. And here's where our LCOE maps become like an uncertain quantity when we take into account different investigation or investing strategies relating to risk aversion. So in general, seismic risk is of course higher near urban centers, but the heat credit is lower if you go too far from the urban areas. So it's kind of a trade-off. Okay. So finally, the output of this analysis is then, this favorability corridors and not the geological targets directly. But what we saw, for example, in densely populated areas such as the Thurgau canton, drilling depth and the geological settings are main drivers of the cost. So we identified favorability areas mainly here in the southern part. Okay, so then we moved to the weather reservoir scale for building our structural model for the favorable areas. However, in our currently investigated joint case study, so the canton of Thurgau, we actually remained for this parallel part still on the regional scale, as the conceptual idea of the geology and also the large-scale seismic survey that was conducted allowed it. So here we start in Thurgau from available legacy data and models. For example, we have several cross-sections available from the local authorities. You also see it here, how they relate to the Thurgau area, and also the red dots, boreholes with or close by the Thurgau area that we could use, and then georeferencing all the available information. All the information can be combined in a GIS system. This is how the different profiles here look that we got. But apart from that, of course, as usual, there's also different ideas of the region. From another source, for example, we have this other subsurface model that says in the region it can be expected that these dark brown structures here are so-called permo-carboniferous troughs, which are not yet included in this large-scale cross-section model that we've seen before. But these troughs are actually particularly interesting to our project, as these troughs coincide, or it's believed that they coincide with high heat flux at the edges. So that is something that can be then combined with our standard model and how we approach this modeling. Florian just showed this before, how we build such a 3D structure geological model with the available information. We do here implicit geological modeling. That means we can set interface information. We use implicit modeling to build a model that is flexible to include further information and do a re-interpolation. It can also be included sequentially. And second, as also previously said, it allows to introduce uncertainties to where interface positions are uncertain and do stochastic modeling of the subsurface, and then to allow some kind of uncertainty quantification from that. And then you derive a 3D model, and drawing then different realizations from this uncertain interface and orientation positions, we derive an ensemble of possible subsurface realizations, representing the subsurface while respecting our uncertain interface information that we included. Can be, for example, represented by such spaghetti plots of where each line corresponds to one realization of the subsurface. In parallel, the seismic campaign took place in Thurgau, according to our workflow. In parallel to the structural modeling, there we did used the so-called NANT technology. This stands for Nodal Ambient Noise Tomography. So why we did use this? It's a passive method that uses the seismic noise that is already there from traffic, industry, wind, weather, and ocean noise, and no extra sources needed. And this is especially beneficial for populated areas such as Thurgau. And it's a cost-effective technology and relatively fast to conduct. And then the output is a subsurface model in terms of shear wave velocities. This model reflects contrast in shear velocity, for example, as we expected between sediments and the crystalline basement. In spring 2025, so last year, a campaign for passive seismic was led by the team from the University of Geneva, and doing deployment of the nodes across the entire canton. Here, each dot represents a nodal seismometer. And looking at the results, we can look at slices or different transect. So first, here we see into what we can do in 2D is, for example, look at shear velocities at different depths. Here's, for example, 1.5 kilometer. It's like slicing through the subsurface. Or we can also look at profiles of interests in depth. Again, here we, for example, have a conceptual model for this A to A prime profile. And this shows a velocity anomaly where we also expected this trough if we do some interpretation here already of lines and troughs. And to make this even more clear, we can overlay this with the inversion, with the conceptual model from before, and you see that this anomaly coincides with the expected contrast in the shear velocity for the trough. So some promising preliminary results. But yeah, we will do more sophisticated inversion. And as you also know, inversion results are usually non-unique, and one single image is not the only configuration of the shear velocity distribution that fits the passive seismic data equally well. So that's a common issue in geophysical imaging, and this issue can be tackled by using probabilistic inversion methods, which then gives us actually an ensemble of possible shear velocity models of the subsurface that fits our data. And here's then where we want to move from separate subsurface models, the ones based on shear velocities, and the other ones, other ensemble based on our structural geo concept, to one joint model that includes the information from the passive seismic inversion. And how do we do this? There's not yet a standard way of bridging this gap, and it's often done in an ad hoc manner, just drawing lines into the seismic inversion results. In GeoHeat, we currently test, so that's our current point of work to work on, a novel approach to do so. It's an adaptation of data assimilation principles, like the interpolation method used in implicit modeling and available data, for example, the geophysical results, but also other types of data is then incorporated via sequential assimilation steps to then derive this joint probabilistic model. This is currently in a proof of concept phase, where we try to understand how this works. So imagine you have a very simple geomodel where interface depths are unknown, so several realizations here with the red lines in this a priori plot, and then you do some kind of assimilation and hopefully derive a posteriori more certain interface locations in this spaghetti plot. Another way to look at this in terms of probability is then the option to look at, for example, how certain an interface location is at a certain location, or a structure at a certain position before and after data assimilation. So what this is outputs is actually an ensemble of geological models that includes the information that was included in the geophysical data, or other data like borehole could also information can also be assimilated. So what we do with that output is then we give this to geomechanical simulation to select the optimal borehole location. So this is done by using the geomodels, the joint ones, and some information from seismic data, for example, fluid presence, to then output here stress fields, fault stability, permeability, and finally also an assessment of borehole stability. Yeah, using several realizations of this joint structural model, this geomechanical assessment remains uncertainty aware and can then be used to update the LCOE map or model and to define optimal borehole locations. So this is where we then end up here at the next step, going to borehole scale. That will be covered in a minute by Alexis. And just wanted to also give some insight to our communication and dissemination strategy, being involved in this huge seismic campaign. The project got some media coverage by newspaper and also by TV. And we also looked into public outreach with the aim about communicating about deep geothermal and particularly the methods we apply at the surface as also novel tools for the exploration, deep geothermal exploration. And apart from the presence in the media, we also aim to reach some public awareness. We already conducted a public survey, I think early 26, so just happened, assessing the knowledge and perceptions, acceptance and misconceptions about geothermal energy. A kind of stakeholder mapping is ongoing with identifying key actors and their interests. And we aim for public information to use also 3D tools, for example, the software Liquid Earth, to allow us to communicate the complex subsurface structure in an intuitive VR environment to the general public. Okay, so in alphabetical order, all the people involved in our work package in GeoHeat. And let me know via the chat or later via email if you have questions. Okay.
Thank you very much, Christine. So if any of you have any questions, please put it into the chat. And I now introduced our next speakers from GeoHeat project. It's Alexis Shakas and Linus Villager, who will make a presentation, high-resolution characterization at a borehole scale for deep geothermal. Please, the floor is yours.
Yeah, thank you, Julia. I will start with the first ingredient for this high-resolution borehole model, which is not this one. I find it. Here we go. So as Christine just mentioned, we are now in the borehole, and it's all about this high-resolution borehole model. And the first ingredient is rock properties. So yeah, it's very important to get these rock properties. I speak of elastic properties, thermal and electrical conductivity, permittivity, and permeability. The electrical properties are specifically important for also the modeling with the GPR then, which will be introduced by Alexis in this presentation as well. And yeah, this is work performed by Fraunhofer IEG, by Eric Senger's group. And yeah, the idea is to get these rock properties from small drill cuttings, so from destructive drilling. And yeah, the why is pretty clear, because coring is expensive and requires an interruption of like this conventional drilling. One important point here is that we need to validate if this approach we call digital rock physics is valid, and we need to better understand if the properties of these drill cuttings are changed due to cutting formation or due to the migration to the surface. Explaining digital rock properties. So first step is getting a high resolution CT scan of this cutting. And then a subsequent step is the geological segmentation, where we distinguish between pores and solids and minerals, and then assign in a third steps the respective properties to these different phases. And finally, it is then another modeling approach to kind of model the bulk of these different properties. That's digital rock physics in a nutshell. Yeah, I go over now to another ingredient, and to another ingredient of this high resolution borehole model, and that's induced seismicity. So the idea here is to identify hazardous faults, and you may remember that this borehole model has an extent of maximum 100 meters or so. That's due to how much the electromagnetic wave of the ground penetrating radar is reaching into the formation. And yeah, it's the seismicity, the used seismicity is just another ingredient or another constraint we want to have. And specifically, we want to obviously identify these hazardous faults we map with the GPR. And for that, we try to automate and improve the seismic processing workflows. And we also want to integrate this new, rather new technology of distributed acoustic sensing into the workflows. So that means on one hand, we perform denoising on DAS data. Usually the noise floor is a bit higher on this DAS data. And then we also want to integrate the DAS lines into conventional detection workflows. Maybe first I quickly talk about the denoising. That's work from University of Pisa, from Giulio Pascucci. Denoising algorithm needs to be fast, so computationally efficient, it shouldn't distort the actual seismic signal, of course. We experiment here with spectral subtraction and non-local means algorithms. The later is from the imaging processing world. And first results you can see on the right-hand side. It's a seismic event induced, hydraulically induced in the Bedretto laboratory, an underground laboratory here in Switzerland. A rather low magnitude, minus 2.7. We were rather close to the hypocenter. There's already a publication out on this spectral subtraction method from Giulio. As said before, denoising is the first part. Then we also want to integrate these, we call it hybrid networks. So that's like standard seismic networks with these new fiber optic lines. And the first thing you actually have to do is you have to reduce the DAS data. Another colleague of mine, of us, Emanuele Pozzi, developed a package which does that. He calls it Orion. So that's the first step. And in the second step, we then use waveform-based stacking methods to actually locate the seismic event. Another package, it's called Lion. On the right-hand side, below the overview plots on top, you also see first results of Bedretto again. Bedretto is very well suited because we have quite a dense monitoring network of all kinds of sensors and also induced quite some events. So and with that, I hand over to Alexis, and you will hear more about the GeoRadar.
Yeah, thanks. So, can you hear me? Can you see my screen? Yeah. Do you hear me?
Yes, we do. Yeah. Yes.
Okay. All right, I tried to do it in the 5 minutes we have left. So we, as GeoHeat, as you heard in the beginning, we have this GeoRadar as a central tool that we propose for exploration. And now we are in this part here where we basically have drilled a borehole and we want to characterize and we want to optimize a reservoir based on knowledge we get from this borehole. And it's a bit of risky proposal what we do because we put drilling or exploration drilling in the prospection workflow. And to basically surround that, we propose to adopt and innovate on GeoRadar technology for geothermal. So GeoRadar, for those of you that don't know, it's basically a tool that also exists for boreholes where you, it's a radar system. So you send radio waves and you can determine distance and direction of objects. So in this case, we're interested in geological structures like faults and fractures. And GeoRadar typically uses megahertz for this. So megahertz, for those of you that have been around long enough to know, are essentially the same frequencies that we had in FM radio, and that is disappearing slowly. But we are working on those frequencies, about 100 megahertz, So these tools exist, but they're about 3 decades old. The company that made them is one of our partners, and they only go up to 200 meters in depth. So what we want to do is we want to develop such a system for geothermal, and I'm just going to show you a little bit now before you see the data set of how this thing looks. So it's a radar antenna, you have a receiver and a transmitter, you lower it in a borehole, and essentially you send out an electromagnetic wave, as you see here in the animation, and this gets reflected by dielectric contrasts. And the electric contrasts in the deep subsurface are usually linked to permeability because water is a very strong dielectric contrast. So we image mainly fluid-bearing fractures that are of course of interest for geothermal. At the same time, we get a 3D data set and we project it into 2D because of azimuthal ambiguity that the antenna has. And then if you have, for example, a fracture that crosses the borehole, it appears as this V-shaped pattern, whereas a fracture that is, let's say, parallel to the borehole will just appear as a line. Here you see another example of such a data set from the Bedretto lab that Lino just mentioned. You see this V-shaped pattern, you see the other pattern, actually I highlight them here for you. And this is for the system that exists already. So we can go up to 60 meters in granite, and we have very high resolution of how these structures look. So for GeoHeat, we are collaborating with Guideline Geo, a company based in Sweden that is, I would say, one of the leaders in georadar technologies. And we are developing a system that has a much higher signal to noise ratio because of newer, basically, electronics that they use that have not been put in a borehole. And we're also developing the system to withstand 200 to 250 degrees Celsius and 700 bars, so about 5+ kilometers. It's a split system in a transmitter and receiver, and you lower it into the borehole with a winch. This is how the prototype looks. So obviously you cannot put that in a borehole, but we are basically developing all the electronics. And actually now we're in the process of making the electronics small enough to fit in a borehole. At the same time, we have another company called ALT, Advanced Logic Technology in Luxembourg, and they are developing the housing for such a system. So it combines titanium, but obviously you cannot put an electromagnetic radar antenna behind titanium because it will just block everything. So the antenna is made of a composite housing. We are looking at different materials. We are actually advancing quite nicely here. And we are also using a Dewar flask, which is the same idea as a thermos. It has a vacuum here to shield from temperature and a heat sink to extract the temperature that the electronics make. ALT is very well suited for that. They actually already have a tool, the QL85 API. It's an acoustic televiewer that allows you to, that goes up to 300 degrees. And actually this tool is meant to complement our radar antenna because ATV, or acoustic televiewer, gives us orientation. So along with the orientation, we basically diminish the azimuthal ambiguity that radar has, and we can create structural geological models at very high resolution around the well. So we're developing such a system, and we're aiming, as I said, these are temperature plots. We're aiming to 200 to 250 degrees, and of course, it depends how many hours we stay at those temperatures. We're aiming for about 12-hour run times to be able to log deep wells at very high resolution. And at the same time, we're also developing modeling frameworks to deal with the data and to be able to process the data that comes out of this. And this is in collaboration with TU Delft and ETH Zurich. We are developing essentially semi-analytic solvers that are based from existing finite difference solvers, and then they can model this interaction of electromagnetic waves with very thin reflectors that can be very far away from the borehole. And to come back to the figure again, we have this last part, which is the multi-scale integration, where we want to essentially take what information, this high resolution data we get from the borehole, and feed it back into the geological or the upscaled model that we have that Christine presented. And here we have a workflow, but for the sake of time, I don't go through every little step. But essentially here, and we have not actually started this yet. This is going into the 3rd year of our project. It's going to start this year. And we take this high resolution information created from radar and upscale it, take the seismic risk, and then use that as a decision-making tool of how to basically engineer a geothermal system. And that's it from my side. And I'm happy to answer questions later.
Thank you very much, colleagues, for your presentation. And following our agenda, so let me introduce the next speaker. Is Diane Tyne from Progress Project. So please, Diane, go ahead with your presentation.
Can you see my screen now?
Yes, we do.
Okay. Right. Hello, everyone. My name is Diane Tian, and now I'm as a postdoc researcher at GFZ from the geoenergy sections. Today, I would like to introduce you about the Progress project, which focuses on the thermal, hydronic, mechanical, and chemical capital modeling of the mushroom-cake diagenetic process, and also the reservoir simulations in the North German basins. So why mushroom-cake as a potential geothermal storage, and how is the THMC framework coupled? How is the large scale models with very high heterogeneity, how it's going on in this project? So now maybe we also have some potential collaborations, maybe with go forward. So I will shortly introduce here. So we know the demand for geothermal energy is increasing, and the mushroom-cake formations on the Berlin-Brandenburg area has great potential for geothermal use in this area. This figure shows a symmetric subsurface model for geothermal doublet systems. And this project aims to test around 100 possible doublet systems in order to assess the geothermal potential in this area and support future site selections. So why mushroom-cake? So mushroom-cake has high potential for sustainable geothermal use. For example, relative high permeability and porosity. It can also support continuous geothermal circulations for both industry and residential buildings. So what we need to understand behind the mushroom-cake formations. The diagenetic process of the mushroom-cake, like domination and dissolution, have strong impact on porosity and permeability. This will directly affect the heterogeneity and all the other physical conditions. In the end, it will affect the reservoir performance. Therefore, so our GFZ worker package focuses on the development of the diagenetic process models and also the THMC coupled modeling process of the mushroom-cake, and do the basin scale and the reservoir scale numerical simulations. Therefore, our project combines geology modeling and real use cases through collaboration with Fraunhofer and GASAC. Fraunhofer IEG focuses on the stratigraphic modeling and the structure framework. So, we also have our industry partners like GASAC provide some practical cases and define the operational boundary conditions and support the assessment of the geothermal potentials. So this project is supervised by Dr. Guido Blescher at GFZ, and I'm also working on this THMC coupled framework setup. And our expertise include multi-physics coupled modeling and numerical simulations from lab and to field scales using finite element method. This project, this objectives of this project has some challenges. For example, it has very high geological heterogeneities, and it has a complex THMC coupled mechanism, and it needs very high computation powers. And also the time-dependent porosity and permeability evolutions that directly affect the geothermal productivities. So based on these challenges, the main objective is to develop a THMC coupled modeling framework to simulate the diagenetic process and the multiphysics process in the geothermal reservoirs. And we want to quantify how this THMC coupled parameters and the mechanisms, also the geochemical process influence the permeability and the porosity. And in the end, we try to apply the Bayesian and the reservoir scales to assess the geothermal droplet performance. So to reach our goal, so we face several challenges. For example, the complicated THMC process has crossed the different time and the spatial scales. We also needed to ensure like the stable data parameters exchanges between mechanics and the water flow and also geochemical servers. We also needed to manage the high computation cost, especially for Bayesian scale simulations with many nonlinear physics and the chemical variables. So how do we do this? We use Golan simulators, which is based on the Moose-Finnan element method. And we coupled it with the frequency for the geochemical part via the I-frequency interface. So each step works like this. And so first, the Golan solves the thermal, hydronic, and mechanical fields. Then the temperature, pressure, and the chemical spatial data will pass to frequency. In the frequency, then it computes the chemical reactions like domination and the calcite dissolution. Then the updated porosity and the permeability chemical concentrations will back to the THMC. So this process enable our fully coupled THMC framework. So for the coupling framework validations, working group at the GFZ did a great job on this development of this coupling. They tested the THC coupling as shown in the pictures. The assumption is the water flow or the water injection is from the left to right. And the results showed that the Golan frequency simulations match the expected behavior under both equilibrium and the kinetic conditions compared with frequency. So based on this THMC coupled framework, we use this strategy graphic modeling comes from our project partner from Fraunhofer IEG. They developed a forward stratigraphic model, as mentioned before, previous presentations, using process-based simulations to reconstruct the Mushakak deposition patterns, for example, the input subsidence and also the state level curve and the hydrodynamics. So then the 3D features architecture, which can be served as the geological geometry for my THMC coupled model and the reservoir modeling. Here is this video. It's an animation from our project partner from Fraunhofer IEG showed how the Mushakak layers and all the other layers built up over time. You can see how the sea level changes and the sediments production shift to the final features architectures. You can see the stratigraphic evolution over around 240 million years. So this slide print the 3D features model include the Mushakak formations under the Berlin-Brandenburg area. Different depositional features are defined by or are assigned by different petriferics properties. And also defined by features dependent porosity and permeability. And then this model will convert into a numerical mesh are used as an input for later reservoir and Bayesian scale simulations with THMC coupled process. This slide also shows the permeability distributions. It shows this Bayesian scale, reservoir scale has very strong heterogeneities. The ongoing work, so we are focusing on more on the THMC coupled framework setup and we already did some small tests with THMC coupled process and simulations. We more focused on this permeability and porosity evolutions over time, and also did some sensitivity analysis to evaluate the THMC behavior of the mushroom. So, yeah, to conclude, this work, we are working on the process-based THMC coupled modeling and for geothermal reservoirs, and we wanted to quantify the diagenetic process, which is control the porosity and the permeability evolution. We also will do the reservoir and the basin scale numerical simulations with stop-plate systems to evaluate the geothermal performance. Yeah. So looking ahead, the next step should be do more THMC coupled simulation with larger scale and under realistic operational conditions, and do some systematic and uncertainty analysis and the application to a regional scale to help to do the geothermal assessment on the Brandenburg area. So this is the last point I would like to mention. The Go Forward project to focus on the VM basins and the Paris basins. This stratigraphic models for Manasseh and the VM basins are also focused on this diagenetic process, and also they can provide the features model that is highly relevant for progress project, for my project. We have this similar objectives, and we can use this features model to do some THMC coupled modeling and the basin scale numerical simulations to evaluate the geothermal performance as well. So this model, this stratigraphic model from Go Forward can be very useful as the input for our model analysis and for later larger scale analysis. So this work might be some interest for related geothermal studies or projects. Yeah, thank you for your attention, and looking forward to your feedback and collaborations.
Great, Diane. Many thanks for sharing your project's experience and ongoing work. So the next presentation addresses 3D geothermal exploration in the Libre Geothermal Village project. So please, Walter Wheeler, go ahead.
Okay. Do you see the first slide here?
Still not.
Oh, wait, I haven't. I'm sorry. I haven't shared my screen. Yeah, let's see.
Yeah, now it works.
Yeah.
Yeah, you just need to go into presentation mode.
Yes. There we go.
Perfect.
Okay.
Thank you.
This is a quick trip through 3 or 4 sites in Africa, which are our sites for the Geothermal Village project funded by Libre, a co-fund. So the 4 sites are here in East Africa. You see the East African Rift with the western branch and the eastern branch. And we have 2 sites in the Afar Triangle, basically. One in Ethiopia, one in Djibouti. We have a site at the edge of Lake Victoria in Kenya, and we have a site in Rwanda. And just to go quickly through this, the fundamental aspect of the project is to do initial exploration but the basis really is the social sciences. So the question is, what does the community want? And these are off-grid communities, either off-grid because they essentially can't afford to be connected, or off-grid because they are maybe 70 kilometers away from the nearest tie point. So what does the community need? Then there's the exploration for the heat and modeling the grid, feasibility studies, what's it going to cost to put in a pilot, and all of that is within LEAP-RE. LEAP-RE is over except for dissemination for this pillar 2. So we're looking for funding for a demo. This is everything you can do with geothermal, direct heat and electricity. So we all know this, don't need to spend much time. But it looks like a nice developed village with greenhouses and fish ponds and agriculture. But if you look at the picture over on the right, not the ORCs, the off-the-shelf ORC gensets, but this one with the cow, a rather skinny cow, there's a lot of development before it's going to be a proper village. Okay. I'll skip through this slide. It shows who's who in the project. What I'll do is I'll say that in red, we have the 3 principal investigators behind Geothermal Village, who've been working on this for more than 10 years. And the project itself was run through the University of Lorraine, Nancy, and by Yves Giron. And his team were responsible for most of the geologic and relatively shallow geophysics work. So if we start with Ethiopia, with Iriboru, you see steam rising out adjacent to a fault scarp. So the point is, well, because of the war in Tigray, and this is on one of the major roads into Tigray, and because of COVID, we didn't really do much with this site in terms of geophysics and geology and geochemistry, except use an IR drone here. So what you see is the hot spots in red, and what you see is that the heat is in the hanging wall of the fault. This is not rocket science. The Ethiopians discovered this thousands of years ago because that's where they built their pits to get steam, to condense it using acacia branches. And, well, next stop, a bit to the east in Djibouti, on the Djibouti shore of Loch Abe. And this is a view at sunset. You see the tufa, the towers, which are built on hot springs, built at high lake level, and then you see the lake in the middle distance, and you see a volcano on the Ethiopian side. So the village is up here, and it's on Graben system in basalt. And this is all lake sediments over here. And this is going to be important a little bit later because these dark objects in the middle picture are these tufa towers, which are where the hot springs are. And underneath the hot springs, of course, are our drilling targets, but you can't drill, you can't place a heavy rig on the sediments. And you can't really put the wellhead on the sediments either. It has to be on the basalt. And I have a diagram of that later. In fact, here it is. So this basic model existed. There's Lac-Abbé. The village is sort of up here. And you see in the satellite view below, oblique view from Google Earth, you see faults in the basalts and the Graben system. And you also see a drone IR view over here, a mosaic showing the hot springs and water flowing away from them, actually starting here at a series of chimneys. So if we were going to drill to under the chimneys, and the yellow and the blue indicate target areas developed from the geophysics, from magnetotelluric and ERT and IP. It's the target depths are 700 to 1,000 meters, and so these are 2-kilometer well paths, which means it's not very effective unless enough electricity can be made to essentially sell to the grid. So this is a view of the Graben and fault systems used to develop the target models. And here's a view of, on the left, a map of the MT, magnetotelluric solution. And this is just at 50 meters below the surface. Below that, you have two cross sections, west-east and south-north, which cross along the vertical line. So what you see here is lower resistivities in the yellows and very low resistivities in the red, indicating fluid, or interpreted as fluid, and that's where the drilling targets would be. So it's about 800 meters top to bottom on each of these cross sections, and so the drilling targets might be at 800 meters depth, maybe deeper. The other tool, the tool is not just MT, to understand the subsurface and determine where the faults are, and to confirm the interpretation that the tufa is that the hot springs are following faults. We used classic ERT, but run also to get an IP result. So we have the classic resistivity tomography here, but below processed to get processed for chargeability to get fluid pathways. So now we're going south to Homa Hills in Kenya. topographic map on the left with hot springs in orange, the orange dots, and on the right, the view, it's a carbonatitic volcano complex, 2 million years old, and the magnetotelluric survey is shown in the bottom middle at 2 levels. The left 200 meters below the surface and the right 660 meters below the surface. They are processed much deeper. If you look all the way on the right, you see the cross-section goes down to is basically 3 kilometers tall. But the point is that in terms of a village scale project, we have fluid accumulations which correspond to hot springs just a few hundred meters below the surface. So we expect hot fluids. The hot springs are up to almost 90 degrees Celsius. We expect useful fluids at depths we can reach with a drilling rig. This is the last stop. It's in Rwanda. It is a hot spring, which has produced lots of travertine. And so this ugly thing in the middle of the Google Earth 3D image is a mine. This is the regional mine for cement. So they're digging through the travertine, which means we got to see a lot of vertical faces showing the flow paths through the travertine. This is in the accommodation zone between the Tanganyika Rift. If you see it, if you look on the right, Cindy Ebinger's, I think, 1989 publication, between the Tanganyika Rift and the Kivu Rift to the north. So it's a beautiful area. They're all beautiful. And what you see in the middle picture here is the electrode layout for the deep ERT IP. Red and blue are red are the injection electrodes, and blue is the receiving electrodes. And this was not they were independent electrodes, electrode systems. So the system, the high edge of the quarry against the mountain is a fault. And so we have a fault, we have generation of the travertines, and below at the bottom you see 2 MT horizontal cross sections maps, one at 100 meters below the surface, and then to the right 200 meters below the surface. And the cross section above shows the hillside projected fault, which has the hot springs, and at about 300 meters, 200 meters depth, an area of high fluid concentration. Then that's from the MT. This is from the deep ERT IP. And the point of the IP is that one can determine, for example, whether low resistance would be water or whether it would be, for example, clay. So we have resistivity above, low resistivity in red, higher resistivities in green or blue, and then chargeability below. And the red would indicate low porosity basement, grading into higher porosity, more clay-rich sediments. And then maps of the same. The higher porosity in basement here, higher temperatures also along the same fault where we have the hot springs. And that's about it. Let's see. I think there's just one more slide, and that is to say thank you.
Thank you very much, Walter, for sharing your experience with us, your project experience. And yes, let's following our agenda, and our final presentation is on geothermal energy development in France. And I would like to present the Damien Bonte from GeoScan project. So please, Damien, go ahead with your presentation.
Thank you very much. You can't see me. Let's start with that. Can you hear me? If you couldn't see me. Yeah, excellent, brilliant, thank you. And I'm gonna share my screen. No. Wrong one, sorry. I'll do it again, and I give you that. That's the one. Yeah. Is that all right? Can you see my screen properly this time? Yeah, in full screen. Excellent. But thank you very much for the invitation and to present what we are attempting to do in France to try to de-risk deep hydrothermal geothermal system. The overall project is called GeoScan, and it's an agglomerate of 3 different projects that I will go through today. And the 3 project managers are Aurélien Bordenave, Virginie Ham, and Alexandre Stopin, with a large amount of collaborator in all different projects from the BRGM, all internal to the BRGM on that. It doesn't change slide. Here you go. The first one I'm going to show you is just for nice purpose, is just to show you that we've been acquiring some seismic in the west of Paris. So we got some fantastic images of this acquisition time not far from the Eiffel Tower. So that's always a nice outcome to have pretty pictures to show. Just to give you a bit of context, deep geothermal energy in France is believed to be possible in the major sedimentary basins. So you have, I apologize, the maps are in French, but you can see in blue the extension of where we think it's possible to develop geothermal energy. So you've got the Paris Basin right in the north. Can you see my arrow on the screen? Sorry, I forgot to ask. Yeah, so if I point things out, it's just so I don't show things. You don't see it. Okay, so what you have in the northern part of, sorry, I'll go for the pointer. What you see in the northern part is the Paris Basin right there, with all this cluster of very dense doublet that go to the middle Jurassic. That's called the Dogger in France, not clastic, limestone reservoir, sorry. So you have the density here with Paris right in the middle. Then you've got a nice development of systems in the southwest basin of the Aquitanian Basin, with the Pyrenees being like right here on the south. And then you've got a series of sub-basins that are part of the Écresse system that goes from the Rheingraben all the way down to Camargue area. And the only system in there is near Montpellier in Pézenas. Overall, all these systems, there are 73 of them, are covered and produce 2.28 terawatt hours last year numbers, and 80% of this system, of this 73 system, are in the Paris Basin. In addition, we have two deep installation, one in Soultz-sous-Forêt in Alsace, and another one in the Caribbean islands of Guadeloupe, and that's the Bouillon system. We have 19 geothermal research permits that are on the go, 7 lithium research permits, and then 8 geothermal research permits overseas. If I go back to what I was talking about at the beginning, so these 3 GeoScan projects, the idea is, how do we exploit this sediment-based basin and develop sufficient knowledge that we will de-risk for industrials these areas where they can implement geothermal energy. So the first project is what we call GeoScan Hexagon. So in France, Hexagon refers to the metropolitan territory that has an hexagonal shape. And in that, as you've seen, all these basins, and we have segmented them into manageable areas that we think that are geologically coherent. The second one, and this GeoScan Hexagon, sorry, we are using only existing data, so well and seismic. For GeoScan Île-de-France, so Île-de-France being like the Paris administrative region and surroundings, we are working on sedimentary sequence that are west of Paris, where there is a lot of prospects that have been put down in the 19th I was describing before. And we think that there is a need to de-risk this area, you'll see, because there is a difference laterally in the facies of the Dogger. In that one, we used existing seismics and wells, but we also acquired, as shown on the first picture, some additional seismic to cover and have a better quality on the information we're using. The third project is GeoScan ARC. ARC stands for the arcs synclinal that are around the Étang de Berre. So we're in the area of Marseille and Aix-en-Provence, all the way to Arles. And this area, we had some seismic and some wells that have been used, mostly seismic, but not very densely like it was in the Paris Basin. And we acquired some additional seismic, both onshore and offshore on the lake here, that is in the central part of the area that we're looking at. So if I give you a bit of focus on this hexagonal GeoScan, then we started the work in 2024, sorry, in the department of Loiret, where the BRGM is based. So that's this department right there in the middle. That we've extended in 2025 in Centre Val de Loire, so the entire region area, which is this one, the BP2. And then we extended BP5, so to the north of the Île-de-France area, and then BP1, the Bresse, here right on the side to explore another basin. In the Paris Basin, what we actually looked at is 4 different reservoirs that are known and identified. The Albion one, that is a classic reservoir. We have the Oxfordian in the upper Jurassic. We have the Dogger in the middle Jurassic, and then the Triassic reservoir that is classic. The 2 intermediate one, the Oxfordian and the Dogger, being limestone reservoirs, you can see on that log. If we zoom, for example, on the BP2 area, which is in the central part of France, so the southern part of the Paris Basin, we used all data available, which is 88 boreholes that got analyzed. So we had 71 that were from hydrocarbon, 15 from gas storage, and 2 from geothermal. We had, as you can see, a very heterogeneous well data density with a higher concentration in the northeast part of the region and a lower density when we go towards the east. You'll see why in a second. You'll understand very quickly why this density, this unhomogeneous repartition. And then we use all the digital well log that were available, and we reprocess above 4,000 kilometers of 2D seismic data that were pre-70s and post-70 so you see here the age of the different lines. So the kind of result we obtained, and you'll see now why I was saying that there's more wells to the northwest, is because the area is way deeper when you reinterpret the entire area. So we got here a threshold of 500 meters. Everything above 500 meters is not shown, but the deposition, so we're at the bottom of the Dogger deposition here. We have a very deep system to the northwest. So you've got the arrow for the north here in the corner, northwest. And then it goes progressively all the way to very close to the surface because we go out as high as 200 meters. If we look at the thickness of the reservoir is roughly in average 150 meters, but with strong variability, as you can see, between 50 and 250 in both sides of the reservoir, including that deep part right there. So a sub-basin in the Paris Basin. Once we add the geometry, we try to work on both aspects, which are the facies for the resource quality and the temperature that we could expect. So for the temperature, so starting here on the bottom right, we have an average thermal gradient of 30.3 degrees, which is slightly on the lower side for the Paris Basin. The Paris Basin is usually somewhere in the vicinity of 34 degrees per kilometer. In terms of facies, we had several set of wells with all the logs associated, or some logs associated, that allowed us to define the variation laterally of the facies. So we have here we had a result for this region that I mentioned at the beginning that we already worked, and the one we're working on, that are on developing a resource that is most known for further development in France. Quickly going through the Ile-de-France one, so west of Paris. So we had 8 new acquired line for a total of 280 kilometers acquired. We had a retreatment of 220 kilometers plus 1,330, so about 1,600 kilometers of line that were used, historic lines, and then 63 wells got used in that study. We are looking in the same 4 main reservoirs that are between 300 or 800 meters in that area, and all the way down to the Triassic that is right above the basement at around up to 2 kilometers in our working area. In the wells, we extracted, just like for the hexagon geoscan, we had a fascist correlation through the wells that were then developed further using in combination with the seismic. We can see that there is a variability that go again deeper to the right-hand side and shallower to the left-hand side. And we identified for the Dogger, which is the main reservoir here, a slight drift in the porosity that is due to an argillous a clay composition that is getting more and more predominant to the west. But we found that the Oxfordian in that area is a very good reservoir, though it's a bit higher, so slightly cooler. We have some really good interpretation. So showing you that is looking at the clay content. So we looked at two things. We looked at the faults to make sure that we understood better the faults in the area, which wasn't the case. We discovered some faults. Some were reinterpreted to have the right orientation. But you see that there is a complex system of faults, even if they're not large faults, they were very interesting to have a good mapping of them for further development. And then here, what I was mentioning on the previous slide, it's some work that has been done on the seismic to understand better the potential porosity, which has been confirmed by well around this location, where the Oxfordian has been proven an excellent reservoir. So the blue is the bluer it is, the more the better it is in terms of porosity and permeability. And then the last aspect, so this one is much less known for geothermal, and because there was some less exploration for hydrocarbon purposes in this area. But we had to work on two different Cretaceous and an Upper Jurassic reservoir, both of them of limestone composition. And what we did to get a better understanding of this area is to get both an onshore and an offshore acquisition that allowed us to quantify the depth of this reservoir, which were not very well known. And we combined that with some CSEM, which is an active electromagnetic technology that allows us to identify the quality of the reservoir. And we obtain for this area a good knowledge of what is going on, combined with the geological assessment, including field work that allows us to do through analogs, because these systems outcrops in some areas. We understand now better to the point where some development has been done to the west of the lake that was in the middle of our area. And to finish on that, just a conclusion to tell you that we have now in these areas that have been worked on a better understanding of the resource. And we show that the exploration in geothermal, even if things are well known, like it can be, given the concentration of installation, we understand much better and de-risk them in a very clear way what is important and what is not. And both three projects allowed us to further development, that our permits have been put down since things have happened on our site. And that's it on my side. Thank you.
Thank you, Damien, for sharing with us GeoScan project outcomes. So we now have covered all agenda items, although we are slightly behind schedule. So currently moving to Q&A sessions. As you might see, all questions have been posted into the chat and the speakers have addressed them. So if there are no additional questions, we propose to close the webinar. And On behalf of GeoCluster and other projects, thank you all for joining us today and for your active participation, insightful presentation. We hope that this webinar has provided valuable inspiration for you and for the next projects. So please stay connected with us and feel free to join the other community. And don't hesitate to contact us directly if you may have some additional questions or comments or suggestions. Thank you once again, and have a great weekend and evening. Sorry, not weekend.
Thank you very much, Julia, for the organization, and thank you for the presentations.
Thank you.
Thank you all, team.
Thank you.
Yes.
Same.
Thank you. Goodbye.